So I just want to go through and answer a few questions that often come up when I talk about correlation in statistics class. So one question is, what's the deal with positive or negative? Maybe you've played the correlations game a little bit and you can identify that uphill slope is one, downhill slope. But in terms of plain English, well, so anytime you have a correlation, you have a quantitative variable on the x and one on the y. And if you have a positive R value or a positive correlation, what we're saying is as our values for the X variable go higher, go more and more, then values of the Y variable also tend to go higher. So an example might be height and weight. As you get taller and taller, probably your weight also tends to get higher and higher. Not always, but in general, that's the relationship for humans. As we get taller and taller, we just have more mass, and so we tend to be heavier as well. A negative correlation means as you go up and up on the x value, the y value, the y variable's values go down lower and lower. So an example of this might be, this is how much vegetables you eat. Put me up here, the amount of vegetables you eat, and maybe this is your risk of cancer. So the more and more vegetables you eat, the lower and lower your risk of getting cancer. That would be a negative. I mean, it's actually a really good thing. I mean, we use the word negative. It's negative in the sense that as x values increase, the y values tend to decrease. What about this? So what about using an R value for other shapes beyond linear? You certainly can. The R value, correlation coefficient R, it's calculated with any, as long as you have data on two variables for everyone in your data set, you can calculate an R value. The question is whether or not it's meaningful and whether or not it's showing a linear relationship. So in this first case, we see what looks like probably a linear relationship between these two variables. Here in this case, we see more of what's called a quadratic or parabola relationship. Here it's linear, but there's like an outlier out of place. And here it looks like pretty much all the x values, all the values have an x of 8, and then there's this one outlier here. The strange things about these four plots is they all have exactly the same average on the x value, average on the same y value, same standard deviation on x, standard deviation on y, and most importantly, all four of these graphs have the same exact R value. They have an R value correlation coefficient of 0.82. So is that 0.82 meaningful in terms of a linear relationship? Well, for this top left one, it is. For this one, no, the points are actually related much closer than a 0.82. The problem is it's not a line, it's a quadratic. It's following a different curve. So yeah, they still managed to score really high on this linear correlation coefficient, but the better relationship is a different one. Here, the points are actually much stronger than a 0.82 in a linear relationship. It's looking like probably this point was an error. Maybe it was a typo because the rest of the points are so closely following each other that it is a linear relationship, but the real relationship between these two variables is probably much stronger than 0.82. And then here, it's hard to say what's going on in that case. So what does it look like to have a nonlinear relationship? Well, here's a case of chocolate intake, and there's quite a few variables like this in the medical field, which is called a J curve. And the idea is as you get a little bit of something, in this case chocolate, how many grams of chocolate you're eating per week, you get some kind of benefit. So in this case, it's relative risk of heart disease or heart incidence. So by eating a little bit of chocolate, now this may not be causation, but people who do eat a little bit of chocolate, they tend to have lower risk of heart disease. But then that curve starts to go up as you eat more and more and more. If you're eating 500 grams, 1,000 grams, that curve goes up higher and higher, so the risk of heart disease goes up and up. So there's an initial curve where you get a benefit from eating chocolate, and then that goes up and up. And that's the same for various, I think wine has a similar one, at least in certain disease categories. But this would be a case where it's not directly a linear relationship. It goes down for a little bit, and then it starts to pop up instead of just a straight line. And if you're interested, by the way, there's the article itself, Chocolate Consumption and Risk of Cardiovascular Disease. It's called Dose Response Association. Dose is how much chocolate you're actually intaking. Response is the impact on your heart. Really good question is, what is R squared? So R is the strength of the correlation. R squared can be changed to a percent. R should not be changed. So if you have R of 0.30, you should not change that to 30%. R squared can change into a percent. And what it means is the portion of the variance in Y that can be explained, predicted by X. Not necessarily caused, but that's associated with or explained by, predicted by. So if our R squared value is 0.47, we could say 47% of the variance in Y can be explained or predicted by X. The calculation is just, if you have R already, is just multiplying it by itself or squaring it, just like it says. Because of that, because R is between -1 and 1, any of those values, when you square them, will take on a positive value. And so the R squared value will always be between 0 and 1. And we call it a measure of effect size, practical significance. Now, this is going to take on a lot more meaning here in a couple weeks. But it's something that backs up what's called statistical significance. Statistical significance is whether or not we think there's some effect or some impact or some difference. Practical significance is more about how much is that difference or how meaningful is that difference. So it turns out to be a very important measurement. So R squared is a measure of effect size. When we do a correlation, who do those results apply to? So this is data from 2 different stats classes, and they were curious whether dressing formally, so coming to class dressed formally, was connected with how much time a person spent outdoors. The idea maybe if you're always dressing up, maybe you're not so much a nature-y person. And so we got this negative correlation, and that was some good evidence that, okay, maybe the more people dress formally, the less they like to spend time outdoors. But before we read too much into that connection between formally dressing to class and outdoors, we might want to look at a bigger sample or a more random sample. When I asked the same question of a different class, it was also a negative relationship, but it was much, much weaker than we had seen in the first class. So the sample itself that you choose from is going to generalize to the population that's exactly like the sample is. And so depending on what your sample looks like, the results may or may not generalize to a wider population. We'll get into that again more here when we get into some statistical tests. Okay, the final thing I want to do is take a look at actually calculating a correlation. So if I ask you to calculate a correlation, how do you do that? Well, here I have a bunch of data on my sleep patterns. REM is a rapid eye movement. It's a lighter stage of sleep, and it's typically when you do your dreaming. And then we also have deep sleep, which is very valuable for the body to heal itself. So I might wonder, what's the correlation between REM sleep and deep sleep? Does it tend to be as I get more and more REM sleep, I'm also getting more and more deep sleep because they go together? Or is it maybe if I'm sleeping really soundly, I'm getting so much deep sleep that it's kind of reducing the amount of REM sleep I'm getting? That would be a negative correlation, as opposed to positive. The more I get of REM, the more I tend to get of deep. And again, this isn't causing that one's causing the other, but how are they related? Well, it's fairly simple. Equal sign for a formula, CORREL for correlation, parentheses, and then I'm just going to highlight the first variable, which is REM, comma, highlight the second variable, and parentheses. That's how I do correlation. And here I'm getting a correlation of R equals 0.306, so 0.31. So it is positive. The more REM I'm getting in a particular night, the more deep sleep I'm also going to tend. As one goes up, the other one goes up. And I could do it either way. The more deep sleep I get, the more REM I get. Or the more REM I get, the more deep sleep I get. Again, when you flip the variables, flip which is x and which is y, the correlation coefficient will stay the same. The equation of the actual trend line will be different, but the correlation coefficient r will stay the same. So if I have that r value and I want the r squared, I can do equals, take that value, times, and click it again to multiply it by itself. This is my r squared value. And remember, it's okay to turn this into a percent. So maybe I'm actually just going to do it as a percent here. So what that tells me is 9.4% of my variation in deep sleep can be predicted by how much REM sleep I'm getting, and vice versa. 9.4% of the REM sleep that I'm getting can be predicted by how much of the deep sleep I'm getting. So the higher this r value, r squared value is, the better we can predict one if we know the other one.